In this video, I'll explain physics and mathematics of Lorentz force in continuous media, which plays key role in MHD pumps used in metallurgy and nuclear engineering. Previously, I showed two fundamental experiments that demonstrate how MHD pump steers liquid metal. First one was a rectangular setup where current is passed from one planar electrode to another, resembling MHD conduction pump. Second was an axis symmetrical setup where current flows radially from center to outer ring. In both cases, magnetic field is created by a permanent magnet placed underneath, which is producing a couple of hundred milliteslas of magnetic field vertically. Usually, we are accustomed to Lorentz force to act on charged particles in electric and magnetic field, making spiral trajectories. In continuum mechanics, Lorentz force acts on a whole object in question, so regular assumption of all mass and all forces acting on a single point is insufficient here. Thus, Lorentz force in continuum mechanics is a force density defined on all points in a fluid and having units of newtons per cubic meter. Mathematically, formula of force looks deceivingly simple. We take two vectors and do a cross product using right-hand rule. In the first experiment, the case was that simple. We had a z component of magnetic field and y component of current, so force is created solely in x direction. Both magnetic field and current do not change in time, so force is constant in time as well. Ring experiment is a bit more complicated. Their current changes direction in Cartesian coordinate system, so solution might be better formulated using cylindrical coordinates, where current has a radial component. Fortunately, it makes right angles with the magnetic field vertical component at all times, so cross product forms azimuthal forces. In practice, the magnetic field and electric field both have 3 dimensions. That makes the interactions more complex than in my simplified models. Correct mathematical formulation would be with a determinant, which as you can see is pretty perplexing. Moreover, these problems are also time varying. Due to this complexity, the best tool for accurate predictions is numerical modeling software. The one I'm going to use is called COMSOL Multiphysics. Here it will solve Maxwell's equations for stationary case, thus giving us 3D current density and magnetic field, with which we can calculate the forces. So current is flowing from one terminal to another like this. It takes the shortest path and intensity represented by color is more or less constant throughout the path. Magnetic field is pointing upwards like this. Here, intensity of the field drops off drastically, as you can see in this colorful graph. The resulting forces are mostly parallel to the channel walls, and with the highest intensity right in the center between the electrodes. This corresponds really well to the flow we saw in the experiment. If we shift the electrodes to the sides, this is how the current density changes. Now it flows diagonally. Magnetic field remains the same, but the force density changes significantly because of the altered current path. When electrodes are put diagonally, the resulting forces have net vorticity, so the flow, as seen in the experiment, creates a single intense vortex. This result surprised me a bit. Before moving on to the next experiment, let's reiterate. The resulting forces in a liquid metal are shown with red arrows. They are caused by a cross product of current density, denoted in green, and a magnetic field, shown in blue color. Throughout the animation, they at all times make the right angles. Lastly, I also modeled the ring electrode experiment. The current density plot shows current flowing from central electrode to outer ring. Magnetic field source was a bit smaller than the outer ring, but we still get mostly Z component in the most of the area where current is passing. The resulting force is like this. It is tangential to symmetry axis. However, force again is stronger at the bottom part since the magnetic field intensity there is higher. And this is how we get the swirling flow we saw in the experiment. I do have to warn you though. The models we studied in this video were a simplified case of the reality. For example, they do not take into account the free surface deformations or effects of induced magnetic field, which all make life a little bit more difficult. Thanks for watching the video. If you like it, press thumbs up so there is more magnetohydrodynamics content on YouTube. And suggest it in the comments whether you want to see more MHD experiments or numerical modeling of MHD processes.